This is the block command through which you can access the value returned by the ultrasonic sensor. Note that the shape of this block is different from the shape of the block that corresponds to the obstacle sensor, and we already know why. Recall that Snap for Arduino uses this shape for logical values and this shape for arithmetic values. And while the obstacle sensor returns a logical value, that is, true or false, the ultrasonic sensor returns an arithmetic value, the distance in centimeters from the closest object in front of the sensor. The range of this sensor is from 2 to 400 centimeters. What you also need to know is that occasionally a hardware-related error occurs, and in this case, the block command returns value 1000. We are now going to use this sensor, and let us start as simply as possible. We have plugged the sensor into the appropriate slot and we put an obstacle in front of ODI. Each time we want to see the value returned by the sensor, we just click on the block command. Now we are going to do the same, but without having to click in order to check the sensor's value. We are going to create a new variable named distance, and inside a forever loop, we set this variable to be equal to the sensor's value. When we execute this program, the value stored in the variable named distance is updated many times per second because of the forever loop. As we move the obstacle, the value stored in the variable changes. When the obstacle is removed, the next closest obstacle is a wall at a distance of around 134 centimeters from ODI. Now let us write some more code to exploit this sensor. Our first program is quite basic, assuming that the user is only familiar to if statements and loops. ODI moves forward as long as there is no obstacle at a distance up to 20 centimeters. If an obstacle exists at a distance between 10 and 20 centimeters, ODI stops. Finally, if an obstacle exists at a distance less than 10 centimeters, ODI moves backward. This is an alternative way to describe what ODI should do. If the distance to the obstacle is bigger than 20 centimeters, move forward. Else, if the distance to the obstacle is smaller than 10 centimeters, move backward. Else, stop. Let us now write the code in Snap for Arduino. We will put all the cases inside a forever loop. This if statement will take care of the move forward case. The forward case is done. We still have 2 more cases to handle, therefore we need one more if statement. If the distance is less than 10 centimeters, we have the backward case. And finally, the only remaining case is the stop case. The program is complete. Let us now test it. Let us now exploit our sensor by creating a parking sensor. This is certainly more difficult than the previous program. The difficulty lies in the fact that we are going to use timers and variables. A parking sensor produces a repeated beep that serves as an indicator of the space available to the driver when moving backward. If no sound is produced, the area behind the car is free. When an obstacle is detected, the sensor produces a repeated beep, the period of which decreases as the distance from the obstacle decreases. The driver is able to derive the distance from the obstacle based on this period. We are now going to make the description of our parking sensor more precise. We define 4 intervals in the values returned by the ultrasonic sensor. If the value is at least 40 centimeters, no sound is produced. If the value is less than 40 and greater than or equal to 30 centimeters, 1 beep is produced every second. If the value is less than 30 and greater than or equal to 20 centimeters, 1 beep is produced every half a second. Finally, if the value is less than 20 centimeters, a continuous sound is produced. An obvious question at this point is this: why do we need timers and variables to achieve this? Can't we do it in a simpler way? Well, let us build a small part of our program without using variables and timers. We will write the code to create a beep every second, which is what our program should do in one of the 4 cases that we have. This is the program. It produces a tone for 0.1 second, and does not produce a tone for 0.9 seconds. Therefore, this program produces a beep every second. And this is the sound produced by ODI when we execute this program. It is not difficult to write similar code for each case, and then create the final program without using variables and timers. However, this is one of those cases where, as we have said in a previous lesson, simplicity comes with a price. In particular, observe that each execution of this loop takes 1 second, which means that we can check the environment every 1 second, and a lot of things may happen in 1 second, things that we will never know of. It seems that this parking sensor will not be as reliable as we want it to be. We really need our program to respond to external events much faster than this. This piece of code produces a similar repeated sound, without using the wait command, which means that this time the loop is executed many times per second. Initially, we reset the timer and the loop starts. In each execution of the loop, it is checked whether the current time is not smaller than 1. If this is the case, the timer is reset and thus it returns to 0. It follows that during the execution of the program, the time is between 0 and 1. In fact, it may be slightly greater than 1, but this is something that we shall discuss later on, so let us forget it for now. Now that we have arranged for the current time to be between 0 and 1 during the execution of the program, we set the tone to be produced only when the time is between 0 and 0.1, and we silence it when the time is greater than 0.1. The result is a beep sound that lasts for 0.1 seconds and is repeated every 1 second. We have now built the code to handle one of the 4 cases. We need to handle the remaining 3 cases as well. One can think of many ways to write this code, but we have chosen this one in order to keep the program as simple as possible and its length under control. We still have a forever loop, and each time we enter this loop, the value of the ultrasonic sensor is accessed and stored in a variable called distance. If the distance is not smaller than 40 centimeters, then no sound should be produced. Thus, if the sound is being produced, we stop it. In any other case, a repeated beep sound must be produced. The only thing that changes is the time interval between 2 consecutive beeps. In this part of the code, we accordingly set this time interval for each case and store it in variable called period. Inside the loop, we check if the current time is equal to or greater than the value stored in period, and if this is the case, we reset the timer. It follows that the current time will always be between 0 and the value stored in period. If we need 1 beep per second, we set period to be equal to 1. If we want 1 beep every half a second, we set period to be equal to 0.5. Finally, if we want a continuous beep, it seems logical to set period to be equal to a time interval that is smaller than 0.1. Here is why: we stop the beep only if the current time is at least 0.1. If we reset the timer before it reaches 0.1, it follows that the timer will never exceed 0.1 and thus we will never stop the beep. At least, this is the idea upon which this code was written. As we are going to see, this idea will in fact cause trouble. But trouble is just another way to learn, so we will continue and see what happens. After all, sometimes it is difficult to see in advance what might go wrong. But when something goes wrong, we need to be able to investigate the problem. Let us now test this code. For now, the distance to the obstacle is 142 centimeters and no sound is being produced. The obstacle is now moving towards Odie and enters the zone where 1 beep per second is produced. 1 beep per half a second now. We are now in the zone where a continuous sound should be produced, but this is not a continuous sound. What went wrong? Is there an error in the code? We need to investigate this issue. Here is how our program should work in this case. Since the distance is less than 20 centimeters, this condition is false. Thus we go to else and then proceed to the first command inside the else part, which is an if statement. The condition is again false, thus we move to else and then to the if statement that follows. Once again, the condition is false and we move to the else part where we set the period equal to 0.05. Then we check the timer and in order for the sound to start, the timer's value must be less than 0.1. Thus, we have now derived the first requirement for our code to work as we want it to. The requirement is that each execution of the loop should take less than 0.1 seconds. Assuming that this is true, the timer will not be reset, because its value is equal to 0. If this seems strange to you, recall that the timer's value changes every 1/10 of a second. The following animation shows the value of the timer, in regard to real time. Then, the loop is executed again in exactly the same way, and finally the timer will be checked once again. Now we get to the critical part of our investigation. When the code reaches this command, the timer's value should not be 0.1 or greater, because then the sound will end. For the timer's value to be less than 0.1 at this point, we need each execution of the loop to last less than 0.05 seconds. Is our loop that fast? Well, let us find out how fast the forever loop is. We are going to count the number of times that the loop is executed within a given time interval, say, 10 seconds. Counting is something we have seen before. First, we need a variable and let us call this variable, count. We set it to 0 before the loop, and we increase it by 1 each time the loop is executed. Then, we execute the program for a given time interval, say, 10 seconds. We can make this program run for 10 seconds using stuff we have already talked about. Or in an easier but certainly rougher way, we can count the 10 seconds ourselves. Let us do that. When the 10 seconds have passed, we stop the program. The value of the variable called count is equal to 135. Therefore, the loop was executed 135 times within these 10 seconds. How many seconds does it take for one execution of the loop? Well, it follows that each execution of the loop takes about 0.07 seconds. Apparently, the loop is not fast enough for our program to work as we want it to. And now a question: how can we be sure that our investigation is accurate? We have used our logic to get to the conclusion that the loop is not fast enough. But can we prove that this is indeed the problem? The answer to this question is also the answer to the following question: can we reach the same conclusion in a different way? We can, and this is what we are going to do now. In particular, we are going to store the value of the timer each time the sound starts and each time the sound ends. To do this, we will use lists. We create two new variables, named start times and end times, and set them to be lists. Then, each time the sound is stopped, we insert the current time into end times, and each time the sound starts we insert the current time into start times. Then we execute the program for a while and see what happens. Keep in mind that we have placed an obstacle very close to OD, in order to reproduce the continuous sound case. We have now stopped the program. Both lists have elements. Inspecting the start times list, we can see that when the sound starts, the timer is equal to 0 except for one case, where it is equal to 0.1. The 0 values are logical, but the 0.1 value seems strange. The end times list, on the other hand, contains values equal to 0.1 or equal to 0.2. The fact that this list has elements means that our loop is not fast enough. Remember that we wanted the timer to be 0 at that point, in order for the sound not to end. Instead, we see that the timer's value is often equal to 0.1 or even 0.2. The 0.1 value in start times is explained as follows. The start tone command was executed when the timer was equal to 0. Just after the execution of the start tone command, the timer increased to 0.1. Then the add command was executed, which added value 0.1 into start times. The fact that this actually happened indicates that sometimes the time needed for one execution of the loop may exceed 0.1 seconds. Before, we calculated this time to be about 0.07 seconds, but this was an average value. We know now that the time spent per execution may vary. Let us now go to the end times list. As already mentioned, the existence of values in this list means that the loop is not fast enough. In advance, we now know that two consecutive executions of the loop occasionally need more than 0.2 seconds. We know that when the timer is equal to 0.2, the actual time is less than 0.3. Assuming that the timer remains equal to 0.2 when the second consecutive execution of the loop ends, we conclude that each execution of the loop takes less than 0.15 seconds. This means that any event that occurs is detected by our code in less than 0.15 seconds. Said otherwise, the response time of our sensor is 0.15 seconds. If this response time is small enough for our parking sensor to be reliable, is another issue. It is now time to fix the problematic case of our code. One approach is to increase the duration of the beep. This way we will give to our program the time it needs. Based on the values stored in the end times list, we conclude that setting the duration of the beep to 0.3 seconds will do the trick. This parking sensor turned out to be a trouble, but we have learned a lot of things. However, our trouble could be avoided if we had written the code differently. And you should know that in programming, there are a lot of ways to achieve the same thing. In order to do things differently, one should ask the following question: why did we face this problem with the continuous sound case? The answer is simple. The code for this case assumes that the loop runs fast enough. Can we handle this case differently? Well, we can handle this case in the same way we handled the no sound case. This is a simpler approach, and somehow, a more symmetrical one. According to this code, we first handle the no sound case. If the distance is long enough, we stop the tone, in case that the tone was being produced. Else, the continuous sound case follows, and this time, no period is involved. We just start the tone, in case that the tone was not being produced. The remaining two cases involve the introduction of a period, and the code for these cases is the same with the code we have seen so far. We have now reached the end of this lesson. What we have learned is that a programmer has to make decisions, and certain decisions may lead to trouble. When things do not work as they should, one has to diagnose the problem, and being able to do this efficiently is a basic skill for any programmer. It was a tough lesson, and I sure hope you found it interesting. See you in the next lesson.